Hey everyone, I'm Michael Hall, and you're watching Innovation Coffee brought to you by ARM, where we give you a deep dive into the ARM developer ecosystem with special guests and topics that bring you the latest innovations happening on ARM. Today, we're looking back at SIGGRAPH, which happened just last month, and we have some special guests on to talk about that. We've got Richard Wright, a senior graphics software engineer from LunarG, who's going to show us the Vulkan SDK running on Windows on ARM. Then we're going to have Sam Martin from ARM talk about their Moving Mobile Graphics Forward class. After that, we're going to have Jakub Sujak in to talk about the latest KleidiAI and its integration with XNNPACK and MediaPipe from Google. Finally, Pareena is going to give us an overview of the latest learning paths that have landed on the ARM Learning Developer Hub. But first, we have a special guest today. We've got Karen Ghavam, who is CEO and Director of Engineering at LunarG. She just gave a keynote presentation at HPG, the High Performance Graphics Conference, and she's going to share a little bit about that with us here. Karen, thank you for taking the time to stop by and join us today. You recently gave a keynote at the High Performance Graphics Conference in July. How was that conference?
It was actually very interesting. It was the first time I attended that conference, and I found the discussions and paper presentations quite interesting, but mostly the people that were there and the new contexts that I created. I really enjoyed it.
Fantastic. Now, the Vulkan Graphics API is really important for ARM, as is Windows on ARM. So we're really happy to have you on to share a little bit from your keynote, which was all about the Vulkan SDK on Windows on ARM. So I'll just go ahead and turn it over to you and let you run us through that.
Sure. This is clearly condensed and shortened. Just to give you a preview of what I discussed. If you want to see the full keynote, you can certainly follow that QR code. I put a link at the end of the presentation as well. But the keynote, it was a story, and it was a story about the beginnings of the Vulkan SDK and how it went from a rocky beginning to the robust set of tools it is today. And it's also a story about the challenges that LunarG had to overcome in the past, present, and in the future as the Vulkan API evolves. And it's also a story of how the present-day LunarG was formed. And I have to say that being able to give this keynote was really an honor and very satisfying for me, because it was an opportunity for me to tell the story of what I've been going through the last 8.5 years. Not everybody gets that opportunity, so it was very satisfying. So in the keynote, I start out with just some context about who's LunarG and who's Kronos and what is Vulkan, and these things were important for that story. However, I'm not going to go into that detail here. And then I went back about 9 years in time to what I call the existential event that occurred shortly before the launch of the Vulkan API, and this event contributed to the rocky beginning of the Vulkan SDK. And then I cover some of the Vulkan developer tools that are in the SDK, because that additional information about the developer tools gives you a better appreciation for the mad scramble that was occurring 3 months before the launch of the API. And it also gives you a better understanding of the Vulkan ecosystem benefactor. And then I finished the keynote covering some examples of technology changes or challenges that we solved in the developer tools, and challenges that we are going to have in the future that are presenting some interesting opportunities. So about 3 months before the launch of the Vulkan SDK, and the Vulkan API, a transaction occurred between Google and LunarG, and this resulted in the engineering team at LunarG being cut in half. This was what caused the rocky beginnings I have referred to for the first delivery of the Vulkan SDK that we wanted coincident with the launch of the Vulkan API. It was really a pretty daunting and scary responsibility that LunarG had in front of them. And this picture actually was created recently by one of the LunarG engineers using ChatGPT. ChatGPT was prompted to create a picture of the Vulkan dragon terribly confused by the Vulkan synchronization API. And this was the result. Now, got a pretty good laugh inside LunarG, but I saw that picture and I thought, gee, that really represents how the engineering team was feeling 3 months before the launch of the Vulkan API. Now, the good news is those engineers knew what they were doing. The bad news is they knew what the challenge was in front of them. The first SDK did launch successfully with the Vulkan API, coincidence, but it was very limited in functionality compared to what we have today. It only supported Windows and a Linux tarball. And the Vulkan loader and the validation layer, they were very young in their feature set, but they were still useful for Vulkan application developers to begin their development. And a very few elements of the shader tool chain were included in the SDK as well. However, the coordinated launch did happen on February 16th, 2016. And on that launch day, there was so much pent-up demand for both the Vulkan SDK and the Vulkan API that both the servers at Kronos and the servers at LunarG that were serving up the specification and the SDK got crashed due to so many pings and so much initial demand. Fortunately, we were able to get our servers back up quickly, and we were able to launch successfully. So we had a very small engineering team and only 3 months to finish preparing for this launch. And so why did we succeed? And I think the bottom line is that the engineering team was very purpose driven. They knew that the work they were doing would have a broad and positive impact in the industry. And that sense of purpose was strong and very motivating for the engineering team, enabled us to overcome some pretty big hurdles in order to make this launch. Now, it's about 9 years later today. The SDK of today has support for Windows, Linux, Mac OS, and Windows on ARM now, and has a very full set of developer tools that are robust in functionality. The last part of the keynote covers many of the technical challenges that were solved while creating the Vulkan developer tools. Only one of the topics that I touch upon that I will mention here is what I called the GPU-centric universe. In that GPUs are not just for graphics anymore. They're specialized hardware designed for efficiently processing large blocks of data simultaneously, and it makes them ideal for graphics rendering and accelerated complex computations that you find in artificial intelligence and machine learning. So graphics API usage on the CPU is actually decreasing. However, the complexity of rendering is still increasing, and it's via GPU-driven rendering. And workloads are moving to the GPU to take advantage of the performance of the GPU features, and CPU interaction is being reduced. So more autonomy is being given to the GPU. This creates some interesting challenges that we will be working on solving. We've solved some of them, but we have more in the future. So think about the differences between debugging on a CPU versus a GPU. On the CPU, you have the instruction set architecture and you can step through the code, but a GPU can be a black box and it's intrinsically different. Imagine stepping through one of a million items in a massive parallelism environment. So the developer tools that we have today that are cross GPU, they're very useful, but these tools are going to need to evolve for the GPU-centric universe. And for this to happen, cooperation from many partners in the industry will need to occur. IHVs need to work with the people writing the specifications and with the tool developers to find API definitions that will enable good developer tools for the application developers without compromising the power and performance of these new APIs. So that's basically all I'm going to tell you. It's just a teaser. If you want to hear the full keynote, it's on the LunarG YouTube channel. I put the link to it there. And I invite you to take a listen. And that's all I have, really.
All right. Well, thank you so much, Karen, for sharing that with us. We really love the work that LunarG is doing. We've got Richard coming on later in the show to show us a little bit more in depth on this. What can you tell us about what LunarG is working on now? Where are you fitting in the Vulkan work now?
We are actually, some of this is hinted to in the keynote. So in the validation layers, because of the GPU-centric universe, many things cannot be validated on the CPU anymore in terms of Vulkan API usage. You don't know the things you need to validate until it's actually executing on the GPU. And several years ago, architecture was put in the validation layer code for what we call GPU-assisted validation, or validation that occurs at runtime on the GPU. Well, one of the large challenges of that is that to validate on the GPU, we have to instrument the shaders, the user shaders, to check for certain parameter values, et cetera, to do the validation. This can result in what I call bloated shaders that can impact performance, both at pipeline creation time but also at runtime. And so we're going through some pretty extensive performance tuning and re-architecting of this GPU-assisted validation in the validation layers, because more and more validation is going to be moving into the GPU on the future. So that's one of the large areas that we're currently working on.
All right. Well, we look forward to hearing more as that work progresses, and would love to have you back on the show sometime in the future.
I would love it. And thank you.
Thank you again for your time, Karen. All right, so that's the high-level look at things. Now, Richard's going to go and dive a little bit deeper into the Vulkan SDK itself and how it runs on Windows on ARM. Richard, welcome on to Innovation Coffee. How are you doing?
Thanks, I'm doing great today.
Now, you were at SIGGRAPH too, weren't you?
Yes, I was briefly. I was there all day Wednesday for the Kronos Birds of Feather, and actually showed a lot of this off at the Kronos networking event that Wednesday night.
Great. I'm really excited. We've just learned more about the Vulkan SDK on Windows, and you've got some demos that you're going to give for us so we can see it in action. So
Sure.
I'll just go ahead and let you take it over and show us what you have.
Okay, I have just a few slides, and then I can kind of show you the SDK in action. The SDK is not super glamorous, but we're excited about it as well. It allows you to build native Vulkan applications for ARM64 Windows 11. That platform seems to be gaining a lot of traction lately, and so there's been an increasing amount of interest in this, and people asking us for an SDK to build ARM64 native applications that use Vulkan. So the SDK is shipped on July 22nd, actually, at vulkan.lunarg.com. You can grab it right now. It includes both ARM64X and ARM64 binaries as part of the SDK. The native Vulkan loader is ARM64X. It comes with Windows. We also provide some, we also have a runtime installer so you can update the loader. It's also an ARM64X library. ARM64X, what that means is it's a native ARM64 instruction set, but it has an x86-64 compatible interface. So your native, I'm just going to say Intel instead of x86-64 every time, but your native Intel binaries can run on a Windows 11 ARM machine, and it can load ARM64X DLLs and interface with them. So your Intel binaries that use Vulkan will run on a Windows 11 machine. It'll get a native ARM loader, and it'll get a native ARM installable client driver as well, the Vulkan driver. And of course, if you build your applications for native ARM architectures, they will also load a native ARM loader and get the native ARM driver as well. So that's pretty exciting. The whole tool chain is ARM64, so your shader executables as well as shader libraries are native. There is a little bit of performance overhead to emulating Intel code on ARM, but if you build for native ARM64, all your shader tool chain and everything will run at native speed. So that's pretty good. It does have native support for the new Qualcomm Snapdragon, which also has native Vulkan support as well. And I've tried it out with the Microsoft DX12 Vulkan implementation, which is later on top. Now, the SDK is beta right now. We plan to be out of beta by the next SDK release. I won't say when that's going to be, but we should be out of beta then. We're currently missing Graphics Reconstruct, a native version of Graphics Reconstruct. I should say the old x86 or the old Intel version of Graphics Reconstruct does work, but we don't have a native implementation fully tested and vetted yet, so we didn't want to ship that with the SDK. And the DXC toolset is also not available yet. The DXC toolset will also be available in a future, probably the next version of the SDK. If not, I'll be in trouble with my boss. So we're going to try to get that out. When you install the SDK, if you've never seen the Vulkan SDK installer, the Vulkan version, the ARM version works just like the Intel version. Same features, tell it where you want to install it. Pretty much the same list of installable optional modules. The one module missing here is the 32-bit module because we don't support 32-bit ARM building. If you're building brand new applications, you should not be targeting 32-bit either, but I won't preach about that. So it goes through the normal installation process, and then other than that, everything is pretty much the same. The Vulkan configurator, it's exactly the same Vulkan configurator. We didn't have to tweak it for ARM. It's exactly the same interface you know and love from Intel Windows. You can run VK-Cube as a sanity test. We also ship the Vulkan hardware compatibility hardware caps viewer, I should say. I'm just kind of highlighting it's detecting the Qualcomm driver and giving you all the information about it. So this is a great tool that you can use to get quick information about the capability of your local driver. And it works flawlessly and transparently with DirectX, Direct3D12 over Vulkan, and even Direct3D12 over Vulkan. I should say Vulkan over Direct3D. Sorry about that. But even works with the software backend Direct3D. So if you need a reference, kind of a quasi-reference software Vulkan renderer on ARM, this will fit the bill. Other than that, installing the SDK is exactly, it works just like it does on Windows. Let me just give you a couple of proof of life demos. This is the Vulkan configurator, which is the best way to manage your Vulkan validation layers and other utility layers on Windows or any other platform. And it comes with the SDK. And just sort of as a smoke test on any platform, you can launch VK-Cube and load the API dump layer, and you can see the layer is, it intercepts every Vulkan call and logs it for you, so you can see, check your code paths or things like that. Also really interesting, now this is a native ARM version of VK-config running a native ARM version of VK-Cube. For giggles, I compiled VK-Quake. And let's switch to the full Kronos validation layer for VK-Quake. Quake is an old game that I used to play when I was a young man, and there's a Vulkan version of it. And this is actually an Intel build. This is a x86-64 Intel build of VK-Quake, and it is running on this machine using the native library. Here's what I'm going to do. I'm going to stop that and do it again. I need to clear my console. Oops. Launch. There we go. There's VK-Quake. All right. So now I'll go down here and I'm going to show you VK-Quake actually has a couple of validation errors. Looks like, the coloring outside the lines a little bit on on some of their shader code. And that's fine. It appears to work fine if you want. I like to leave Vulkan configurator running all the time while I'm doing Vulkan development. So I'm going to leave it running and show you a real demo from something that happened to me. Like most Vulkan developers, we like to make our own toolkits, so to speak. So I'm working on my own high-level toolkit, and then a demo program that exercises the toolkit and that I can use for testing. And I came across a validation error when I ran it on Windows. Let me go to the folder. My demo is Orrery, which is 3D model of the sun, Earth, and moon because I'm an astronomy geek. And here's a CMake list file. Apparently, I opened it twice. I'll just show you here. And right here, find package Vulkan. This is exactly the same CMake file that I use on Windows, Intel Windows, and actually on my Macintosh as well. It's exactly the same file. Find Vulkan works. It finds the SDK just like it does on Windows 11 Intel. And here's some libraries that I'm using from the SDK. It's using SDL2, Shader C combined. It's part of the shader toolchain. It comes with the SDK. It loads your shader files and compiles them to SPIR-V for Vulkan. Works with GLSL, also works with HLSL. There is a debug version of this, so don't judge me too harshly. This is my own pet project. It's not public yet, but I'm just linking to the release libraries and building. And well, let's build it in C. CMake ... I'm in the build directory already. You can see I kind of prepared for this demo. And the CMake's already done. And it built a Visual Studio solution for me by default. I could probably compile it. Well, I know I can compile it from the command line, but let's just load it into Visual Studio and run it. And I'll show you a validation problem that I had the first time I ran it. It doesn't take very long, 20 or 30 minutes here, and it'll build the whole thing. I'm just kidding. It's just almost there. And this just Visual Studio is Visual Studio, whether you're on ARM Windows or Intel. And here's my half-done Aura remodel. Still got a little ways to go. But over here in the console, I can see I got a validation error. What is this? VK swap chain is outside bounds returned by physical device surface capabilities. Min image count 2, max image count 2. Okay, so what's going on here? I set my frames in flight, which is how many swap buffers you have, to 3. And I got away with this on my NVIDIA desktop, and I got away with this on my on my Apple Silicon. But apparently on this device, I can only set it to 2. You can tell from the comment here, But this was a real, oh, look, this surprised me sort of thing. And so I can change that. Let's close my project and run it again. And it'll compile and build, and this time I'll get no validation errors. I'm just sort of dumping some information here, but I did not get the validation errors. And like I said earlier, I really like leaving Vulkan Configurator running the whole time I'm coding because, it does have some runtime overhead, but you can see clearly it's not dragging my frame rate down to make it intolerable. But that helps me find, API coding errors in Vulkan. It's really great when you're learning Vulkan too, and you use an API incorrectly. You can look at the validation error and find out what's going wrong. In fact, I would say, to me, that's like the number one most useful part of the Vulkan SDK is Vulkan Configurator and the validation layers, being able to get that feedback. The shader toolchain is great. It's all pre-built for you, so it's all been vetted. And of course, internally at LunarG, we have our own CI and SDK testing. And so we vet everything before we package it in the SDK. But that's it. It's an SDK. You link to the libraries, you run your program, and you're done. So,
all right. Well, thank you so much, Richard, for that demo. Could you tell us a little bit about what the process was of building the SDK and all of its associated tools for Windows on ARM?
Sure. A lot of it was figuring out how to get everything to build for the ARM architecture, that there's a lot of CMake files, and by default, they didn't necessarily build for ARM64. And then in a lot of the build scripts, they call scripts that call scripts that call scripts. And the top script we might know about ARM64, but the bottom one wouldn't. And then there was apparently a very poorly documented, difficult to figure out how to build everything for ARM64X. That's the magic format that lets the loader and the validation layers be used by both Intel and ARM binaries. And so that was a bit tricky to figure out. And then internally, we had to rewrite the runtime installer for ARM64, make sure it doesn't run on Intel boxes and it does everything the correct way. And then we also have some SDK automated tests that we run internally that goes through the whole SDK. It actually builds and compiles Vulkan programs and calls command line programs and checks their validation output. And that had to be massaged. It runs on all three platforms, Windows, Mac, and Linux, but it had to be massaged a bit for the Windows ARM specific version because, it wasn't written. When it was written originally, there was just Intel Windows, and I don't think anybody was thinking about an ARM version of Windows at the time it was created. So it was really very tedious to put together the tool set and the packaging components and to build all the necessary libraries. There wasn't a lot of, I have to fix code in this repository. Most things that build for Intel build for ARM without really having to change anything. It's not like you're going from big endian to little endian or 32-bit to 64-bit or, I don't have to remember 16-bit to 32-bit. That was a nightmare. So really moving to ARM, like my own demos and things, moving them to the ARM platform with that, once the SDK is done, it's just simply selecting the right tool set and recompiling and making sure all your dependencies are also built for ARM as well. There's really not a lot of porting work that has to be done.
All right. Well, Richard, we appreciate all the work that you and LunarG have done to port the SDK over to Windows on ARM. I'm sure a lot of other developers are going to appreciate that work as well. Can you tell us one more time where people can go to find out more about this?
Vulkan.lunarg.com. You can download the SDK for any platform from that. And we also have full documentation for the SDK at that place too.
All right. Once again, Richard, thank you so much for being on our show. We appreciate it.
You're welcome. It's been a pleasure.
Did you know the ARM Developer Program has a thriving community on Discord? It's the perfect space for developers to connect with ARM experts and engineers, seek support in active forums, stay updated on the latest events, and engage in focused discussions on topics like AI/ML, cloud computing, embedded development, and more. Whether you want to showcase your projects, explore the latest ARM developments, or network with like-minded developers, our Discord community has it all. Don't miss our twice-monthly office hours, where you can dive into open discussions on cutting-edge technologies, share what you're working on, or simply listen in and soak up the knowledge. Join the ARM Developer Program on Discord and become a part of our growing community today.
Next up, we have Sam Martin from ARM, who's going to talk about a course that they give at SIGGRAPH every year called Moving Mobile Graphics Forward. Sam, welcome to Innovation Coffee. How are you doing?
All good, thanks. Good to speak to you, Michael.
Now, you were just at SIGGRAPH back in July, is that correct?
Well, this is where we're going to start immediately. I didn't physically attend.
Oh, okay. But this course that you're going to be showing us, that was something that did run there at SIGGRAPH.
Exactly. So it's a course I organize. I have too many kids these days and can't travel so much. So I'm part of organizing a course. A guy called Jesse Barker chaired it for us. I helped organize this course that ran at SIGGRAPH just recently.
Nice. And this has been going on for several years now. Like, when did this course start?
So we're coming up to a decade now. At least we'll have that anniversary next year. So we started back in 2015, which at the time there was a lot of there were mobile talks at SIGGRAPH, which is this kind of big graphics conference. All the leading stuff comes out there. And mobile was getting some support from the SIGGRAPH community to try and make it a prominent thing there. But it hadn't really consolidated into anything. And mobile talks were a bit kind of spread around. One thing that works well at SIGGRAPH is you do get these kind of curated courses, either on like deep specific topics of fluid mechanics or whatever it happens to be, right? And there's a very successful, a couple of long-running series of courses, notably Advances in Real-Time Rendering, fantastically successful course at curating and championing real practical applications of graphics in games. And so we thought it'd be a good idea to do something similar for mobile, right? To have some platform to help champion, across the industry, the bleeding edge of what was going on in mobile graphics, and to try and help bring that all together in one forum.
All right. Well, we don't have enough time to go through the whole course right now, but I would love it if you could give us kind of an overview of it and maybe a little bit of a sneak peek at some of the content that's in there.
Sure. So each year we start off with introduction to mobile graphics. Run through that really quickly to kind of get everybody on the same page. But then each year the course content changes, right? Where you try and get in developers or hardware companies or engine providers. So over the years we've had Roblox, Unity, Epic, EA, 60AI, Qualcomm, ARM, obviously. All Samsung, all participating and bringing forward the best of their work. So this year, ML's a big thing. We had a great talk there from Liam O'Neill on mobile neural supersampling. I think that's a really interesting topic, one we're following very closely. We had a great talk from Seb Altonen from MediaPipe on the work they're doing on physically based rendering. A talk from Supercell. All this works obviously it's great if you can see them live, and you may still be able to get a virtual access ticket to SIGGRAPH to watch them back, but all of the slides and notes are available on the website to download. And you can go back to all the previous years, right? We've got everything going back to 2015, so there's a great archive there of all the material of moving mobile graphics for the last 9 years, and next year we'll make it a decade.
Very cool. Can you give us an idea of give us an example of one of the specific things that are being taught in this course so people can understand the depth of it?
So I guess each of these things is usually some specific learned lesson. Either it might be an industry thing, so experiences. So Timo from Supercell talked this year about their experiences of moving their renderer that powers a lot of the Supercell titles over to use Vulkan and all the kind of transition work necessary. So kind of very almost industry engineering graphics heavy. Whereas in contrast, we had Liam O'Neill talking about work that won't yet even run on mobile. It's about work that of how in the future ML will bring about new forms of graphics, like neural graphics, where we'll be able to do things that we can't currently do on hardware. So we have this kind of research looking ahead at where things will go, and everything in between, right? So we have each year we have a couple of choice topics, if you want. Previous years we've covered VR, for example. There's been a lot of VR, AR topics. A good few years ago, a company called 60AI did very impressive live mobile demo of some of the live world reconstruction work they were doing, where they could walk around with a camera and capture things as 3D objects on the fly. So there's a big mix of stuff. You really just kind of have to rake through and find the kind of topics that you're interested in. I think some of the best ones are actually ones that you didn't realize you were interested in something until it piqued your interest.
Very cool. And so this just ran last month in July. Do you know when the next time it's going to be available?
Yeah, SIGGRAPH's the yearly thing, right? So usually, irritatingly, the first week of summer holidays in the UK, but it's usually start of August. Preparation for this starts quite a lot earlier, though. We submit the course usually end January each year, so good 5-6 months ahead of the conference running itself. And so we look for new contributions towards the end of the year. So we're still in recovery from doing the last one, but in a month or so's time, we will start putting the word out for asking for talks, seeing what people have, what they would like to contribute, and we try and then pull together an industry impartial, best of class set of presentations for the course and submit that as a curated set come the turn of the year. So if anyone's interested in they're working on something cool in mobile graphics, whether it's deep in industry shipping things or whether it's on research end, we'd love to hear from you. Please just get in touch and we'll talk you through it.
All right, fantastic. Any graphics developers going to SIGGRAPH next year, get in touch with Sam here at ARM. If you want to find out more about it right now, you do have a blog post out there that you keep updated every year, right?
Yep. Straightforward, long-running series of posts, the PDFs, and anything we've ever put out there. You can find slides to your heart's content. And some years, particularly during COVID, the whole thing was recorded, and so we actually have all of 2020 up there in its entirety. Everything was on YouTube, so we have all the recordings there to watch, follow along with.
All right, so everybody, go check out that blog post. Get in touch with Sam if you want to be part of this at SIGGRAPH next year. Sam Martin, thank you again for being on Innovation Coffee with us.
Thanks for having me.
Now, back at Computex in May, we announced KleidiAI, a brand new library from ARM to help accelerate machine learning and AI workloads. I'm joined now with Jakub, who's going to tell us a little bit more about it and how it can integrate with frameworks such as MediaPipe and XNNPACK. Jakub, welcome to the show. How are you?
Hi. Yeah, thanks for having me, Michael. I'm excited to be here.
All right, so you're a software engineer at ARM, and you've been involved with this. So you're the perfect person to tell us more about Kleidi and how it's going to be used. So you've got a presentation and also a demo so we can see it in action. So let's just jump right into that.
Right, yeah. So hi everyone. I'm Jakub. I work on the KleidiAI project. And today I'll be presenting to you a lightning talk on the KleidiAI project, what it is we're doing, and how KleidiAI is being used today in AI frameworks to accelerate AI inference. Specifically, I will highlight a success story of how one AI framework, MediaPipe, has integrated KleidiAI and how they've managed to see a significant performance boost on Android devices when running the large language model Gemma. But for us, a quick recap. So we're all aware that AI is very popular right now. And it truly seems that with all these new, amazing, and highly capable large language models being released, that the age of AI has truly arrived and is now making a real impact on our lives. But to be able to make AI accessible to everyone, we need to find a way to bring these large models down from the cloud to your phone or device that you interact with every day, so that everyone can benefit from a deep AI integration in the everyday apps we use. And for this, we need to tackle important challenges around fast and efficient inference of AI models. So the good news is that the ARM architecture is very much suited for AI inference. Whether you may or may not know, ARM has been heavily investing into AI capabilities in the ARM architecture for many years now. From the first ARM Neon SIMD architecture extension to the scalable vector and scalable matrix extensions, SV and SME, there are many hardware capabilities that are available to us to exploit to make heavy computation required for AI workloads a lot lighter. Just going to switch slides. Okay, so this is all building into the mission of the KleidiAI project. So what is KleidiAI? KleidiAI is a collection of performance-critical routines that leverage these ARM architecture features to accelerate AI inference on ARM CPUs. We call these routines microkernels, and they're designed to integrate directly into AI frameworks, where we can speed up both traditional ML and the new generative AI workloads. We're kicking off KleidiAI by adding microkernels to compute matrix multiplication, a core computation in neural network inference, which we optimize in ARM assembly code using modern architecture instructions. The big picture here is that once an AI framework has taken and integrated these KleidiAI microkernels, you will be able to run workloads through that AI framework, knowing you're automatically getting the best possible performance out of your ARM CPU by default and without having to do any extra configuration or setup. The KleidiAI project is open source under permissive Apache 2.0 license, so you can comfortably incorporate it into your own projects. And we provide learning paths on the ARM developer website to help get you started. So I want to highlight today the successful integration of KleidiAI into a popular AI framework, MediaPipe. The MediaPipe framework from Google is a solution to building on-device machine learning pipelines as a means to deploy models like Google's Gemma. The integration point for us is XNNPACK, which from the graphic on the slide, you can see is what MediaPipe uses under the hood as the execution provider. XNNPACK had integrated our specific microkernels to improve inference performance for models that make use of the dynamic quantization and integer for weight, which, as I will demonstrate, is what the Gemma 2 billion parameter model uses. Thanks to these optimized microkernels, we're able to see a significant 30% speed up in Gemma's encoder when running the software stack shown. It's also worth mentioning that XNNPACK is a very popular choice outside of MediaPipe 2, with 7 billion third-party installs, meaning that many applications will be able to benefit from the new KleidiAI optimizations, which are enabled by default in XNNPACK. But of course, we want the community to get hands-on with our projects and learn how to efficiently run LLMs on device. So the team at ARM has prepared a step-by-step learning path for you to try and build MediaPipe with KleidiAI integrated and run it on your own Android device so that you can enjoy the performance uplifts for yourself, and which I will now demonstrate to you how to do in a few simple steps. Just a note, you will find the full guide on ARM Developer. I will paraphrase things here for brevity's sake, but please try the learning path yourself, as the instructions are very easy to follow. So I'll switch over now to my terminal. So, opening my terminal, you will see that I have a Docker file. So this Docker file has been prepared for you in the learning path and has all the necessary dependencies to get you started, including MediaPipe and the Android NDK. Everything is there, as you can see. So I'll just build the Docker image, which I can very easily do with the Docker build command. And as you can see, I've built this image before, so everything has been cached for me. Now, if I run the Docker container and I have a look around, I can see that the MediaPipe repository has been prepared for me, and I can proceed to build the project. We're going to use MediaPipe's Bazel build system to build the LLM benchmark, and I'll point out to you 2 important options you need to enable to make use of the KleidiAI optimizations. So this is the full command. The 2 flags that are important here are XNN enable KleidiAI. This is enabled by default, but I'm showing it here for completeness. And the next flag you'll see is enable ARM i8mm. This means we're employing the Feat i8mm architecture feature, which introduces integer matrix multiply accumulate and dot product instructions. By setting this flag to true, we know XNNPACK will choose to run the KleidiAI kernels that have been optimized with these instructions. I'll skip the compilation here, as the compilation does take about 5 to 10 minutes for me, but I've pre-compiled the 2 binaries ahead of time, one with and one without KleidiAI optimizations, by either setting both of these flags to true or to false, so that we can have a direct comparison. Now, I did mention that we're using the i8mm architecture feature. It's optional from ARM v8.1 and mandatory from ARM v8.6. So if you're using a recent phone, like my Google Pixel 8 here, you should have this enabled. But we can still check if the device does indeed support i8mm by checking the system's CPU info. So if I exit the container, and I go and enter my phone's terminal with the Android debug bridge, I can then print out my phone's hardware capabilities. And I do indeed see that I have i8mm support among a list of other goodies. So that's perfect. And we can now proceed to running the Gemma benchmark. So if you follow the steps so far, you will have built the LLM benchmark binary. You can then move it from your machine onto the Android device using ADB and run it. So that's what we're going to do right now. So here you can see I have 2 binaries. The base benchmark binary, LLM test, without KleidiAI optimizations, and the other one that's been optimized with KleidiAI. So let's run the first one. This will take about a minute to run. You can see that we're benchmarking the LLM with a fixed sequence length, the 5112, and a fixed prompt size, but we are changing the batch size parameter. Okay, that's finished running. In general, not bad, but we can make this much faster. So if I run the same benchmark, but with KleidiAI optimizations enabled, so you can see that we are processing many more tokens per second with KleidiAI enabled. So there you have it, at least 30% performance improvement in the encoder. I hope that you can see what an impact KleidiAI can make in reducing the latency of running LLMs, and just how much more responsive app experiences can be if they integrate KleidiAI.
Jakub, this is amazing because we basically just sped up MediaPipe and XNNPACK on the same hardware, running the same, developer's application for free, essentially, for them, right? They don't have to do anything to their code. They just get the latest version of MediaPipe and XNNPACK with this in there, and it just runs faster on ARM CPUs. And so that means, like, if they're running it on a mobile phone or they're running it on AWS Graviton, they just automatically get that 30% increase in AI speed.
That's right. It comes automatically. It's as soon as any framework integrates it, you will be able to benefit from these optimizations by default.
That is amazing. Thank you for showing this off to us. If somebody wants to learn more about it, what's the best place for them to go?
So I recommend. So that's all for the brief demo today. But I do recommend, and I encourage you to try the learning paths yourselves. There are two: the one I demonstrated today, and another called Accelerate Generative AI Workloads using KleidiAI. That one goes more in depth into the workings of KleidiAI and what specifically is going on inside. And it's a helpful guide if you'd like to better understand how to call the microkernel functions to integrate them into your own framework or project. We also think it's a good idea to have a learning path that shows how KleidiAI can be used in an Android app, and we're actively looking into it. So that's all from me. Thank you very much for watching.
Fantastic. Thank you for being on the show, Jakub. And as KleidiAI gets more microkernels added to it or it gets integrated with new frameworks, we will be sure to announce that on future episodes of Innovation Coffee. Thanks, Jakub.
Thank you, Michael.
All right, now we're going to go to Pareena and see what the latest learning paths are that have just been published to our ARM Developer Learning Hub.
Hi, everyone. In this segment, I'm excited to cover some of the new learning paths that we've published over the course of the last month. So we've had a lot of developments around ARM's newly released KleidiAI microkernels, and we released two learning paths. And I'll quickly introduce the two learning paths around KleidiAI. So this first one is targeted towards Android developers who want to efficiently run LLMs on their device. You'll be able to build and cross-compile a new inference engine for Android. You'll download the Gemma 2B model from Kaggle, and then you'll run an LLM inference on your Android device using Google's MediaPipe framework. The really exciting part is how you will be able to take advantage of the seamless integration of the KleidiAI microkernels in the MediaPipe framework through XNNPACK. So you'll be able to benchmark the throughput performance of your LLM running on your device, both with and without the KleidiAI microkernels, and see the performance impact and the great increase in your performance. So the other learning path that I wanted to talk about around KleidiAI is more introductory in nature, right? And this learning path is targeted for developers to understand what really is contained in KleidiAI and how do those microkernels accelerate the execution of generative AI workloads. So through the course of this learning path, you'll learn how basic math operations power LLMs and how these microkernels speed up the performance of those LLMs. You'll walk through a basic C++ matrix multiplication example, and you'll see the speed up that you can get from these microkernels. So KleidiAI is fully publicly available. The microkernels are on GitLab, and in this learning path, you'll download some of those examples and run through them and understand how you get that speed up by taking advantage of certain features in your ARM processors, like the integer 8 matrix multiply feature. So that's KleidiAI for you. One of the other learning paths that we released is around using Process Watch. Now, Process Watch is an open source tool or utility which you can run on any ARM-based machine running Linux. So you can run it on your bare metal server, a cloud-based instance, or an ARM developer board, as long as you're running Linux in a particular later kernel version. And in this learning path, you will learn how to build and run this tool on your ARM machine, but you might ask, what does the tool do, right? So you can use this Process Watch tool to check in real time whether any workload that you're running on your ARM-based machine is using some specific ARM-based instructions. For example, is your workload using Neon instructions or SVE2 instructions? So through this learning path, you'll be able to install all the dependencies for Process Watch on your machine. You will really understand what Process Watch does, right? If you're familiar with Linux perf, it takes advantage of the perf events interface, and it samples the retired instructions of your workload running on your machine. So then you use the program counter and the process ID for your workload that's being executed, and it decodes it internally and maintains a count for each instruction that's being sampled. So it's a very nifty tool that you can use to identify if your workload has been compiled correctly to take advantage of the right feature sets. For example, if you've compiled your application to use SVE instructions, you can launch Process Watch on your compiled workload. And on that process ID, you can set a bunch of filters to identify if it's detected that the workload was compiled for SVE or if it wasn't. So I urge you to give it a try and try this tool called Process Watch. It's really neat to understand, gives you a good indication of what instructions or group of features of ARM architecture your actual workload is compiled for.
All right, that is our show, everybody. Thank you for tuning in and following along. We'll be back again next month with another episode of Innovation Coffee brought to you by ARM.